Hey, it's Steve. It is April 7th, 2017. The time is 16:47. Temperature is only 47 degrees Fahrenheit out. But the good thing is it's Friday, and by Sunday it's supposed to be 70. So I'll take it. Plus, it's finally sunny out again. After 2 weeks of basically raining, it's sunny out. Now, when I get home, I'm going to have to cut some grass just because I haven't been able to do it in 2 weeks. So that's going to be fun. And I have one of those manual push mowers. But anyway, and I say manual, I mean no motor manual, you know, the spinning blades. But anyway, all right. Today's Geo-Rant is going to be a continuation of the last one. In the last one, I explained how we surmise the interior structure of the Earth through seismic waves. Today, I'm going to talk a little bit about each of those layers and what we think they're made of compositionally and how they behave. So I do have little visual aids to help here. This is a good one. This basically shows the main divisions of the Earth and the distance kilometers from the center. That's a good one. Okay, but that's not the main one I'm going to show you. I want to show you this one. First, I'm going to hold it up, slowly scan it so you can kind of look at it, and then I'm going to talk about it. Try not to bring it up, like lift it up unless I absolutely have to. Called it Earth's interior. As you can see, hopefully the road won't be too bumpy and I don't have my hand over anything. This bottom one I kind of like, even though it's a column. It's basically just like a core, if you were to core to the center of the Earth. That one gives temperature at different depths. This one gives the minerals. I actually went through and added all this stuff on the side. The minerals in each of those layers. So, and it's not exactly to scale. That's from a textbook, and I altered it. Okay, so let's start top down. We have the crust, which is made of the continental ocean crust. As in other videos I've said, you know, continental crust is less dense than the ocean crust, and right beneath the crust is an area called the lithosphere, which is technically the mantle, but in plate tectonics, the plates that move around the globe, the lithosphere and the crust act as one unit. So when there's a subduction, it's not just the crust getting subducted, it's also the lithosphere. Okay? Now, between the crust and the lithosphere is something we call the Moho. It was discovered by some Yugoslavian guy back when Yugoslavia was a thing, and I can never pronounce his name, but we call it the Moho. Basically, that was discovered how all these other layers were discovered. So I'm crossing tracks, and for some reason, people, when they go over decent tracks, they feel the need to slow down to 5 miles an hour. Where is it? Okay, now the Moho and things like the Moho and the D layer, which I'm going to talk about, which is also the Gutenberg discontinuity. These are discontinuities. All these is they were named because of a change in velocity of seismic waves. Okay, that's the top graph there. All right, and I've labeled the Moho. The Moho's really shallow, so it's near the top, but you'll see the D layer down deeper. That's all that means. Obviously, it does mark something because seismic waves would not change velocity if there wasn't a change in composition. But, oh man, my cigarette died. Hold on. Sorry. But we think that the Moho is, it's not it's a true boundary, but we think the crust has a lot of feldspars in it, okay? The Moho might be the division between where we have a lot of feldspars and we don't. We are currently trying to drill past the Moho and actually get into the top of the lithosphere, which is the mantle. We have yet to be successful, so we could actually see at least that, part of it. So there's no felspars apparently below the crust, at least we think. And when I go over these minerals, other than some of the lithospheric mantle we have thrown up on the continents in places through plate tectonics, we don't really have any samples of the mantle. So below that, we don't know for sure what lies beneath there. I thought I had a location in here. Maybe I don't. Okay, so we'll get back to this. Like I said, we could run pressure and temperature experiments on minerals and see what happens. And what we find out is below the lithosphere you have what is called the asthenosphere, or sometimes people call it the upper mantle, but it's the asthenosphere. This is where most of that plasticity takes place, where we get most magmas from. The base of the asthenosphere is now known to contain, it's rich in hydroxyl radicals. I don't want to use the word water because it's not actual water. It's water molecules bound to minerals. And what this does is this lowers viscosity and lowers the melting point of rocks. So, and it seems that as the plate goes down, that it brings some water down with it. Some of that water makes its way back to the surface, some does not. And it gets down to this layer. And the asthenosphere is mostly rich in olivine and pyroxenes, silicon aluminum oxides. But in the middle of the asthenosphere, at about 450 kilometers down, olivine becomes unstable. And we know this through pressure experiments. Another set of minerals takes over that is closely related to olivine, but actually isn't, and it's wadosonite and ringwoodite. I hate those names. I always have because I've never been able to say them. Okay, so those make up the lower part of the asthenosphere. Then at about 700 kilometers beneath where the water included in the minerals is, we get the more rigid mantle. Obviously it does convect because we can tell through, seismology that some of those plates that deep down, they just don't dive into the asthenosphere and get recycled, but they actually go into the lower mantle, which is known as the mesosphere. And then at about 2,700 kilometers to the outer core, we get what's called this D layer. And this thing is weird. Okay, I took this right here from an actual paper. It's cited. The D layer is very bizarre because the outer core is where our magnetic field is generated, okay? And the D layer is that boundary, and it's got great topography on it. In some places it's absent altogether. In other places it's 150 kilometers thick. So, and this changes, but we don't get any deep earthquakes from down there. So obviously this is sort of like a fluid interaction. This might be more like a peanut butter behavior, So this D layer may actually be where those deep mantle plumes are created. There's interaction to the outer core and the mesosphere of the mantle. Okay, then we get into the outer core, which, like I just said, is where our magnetic fields are generated. And it's convective, and it's liquid, all right? And it's made mostly of nickel and iron. There's silicate minerals and things like that. And the inner core is basically the same thing, made compositionally the same, except it's a solid. And the outer core is about, I think it's just the outer core, is about 70% the diameter of the moon. And in the inner core is where radioactive decay takes place, where we keep getting, the Earth should have cooled by now. Okay, the core, everything should have cooled, but it hasn't because of radioactive decay, which generates heat. And the main radioactive minerals in the core, although in very small amounts are enough to do this, are likely potassium, uranium, and thorium. Okay, now I want to get into the. I'm almost done here. This is a little long one, a little longer than I wanted it to be. But if you think about the Earth, the mantle, although from the base of the crust to the outer core is roughly half the diameter of the planet. That's 84% of the mass of the entire planet is the mantle. Okay, the crust, where we live and where we have done our deepest drillings and mines and all that, 1% of the volume of the Earth. And then the core makes up the remaining 15%. So the vast majority, so 99% of our planet is unknown to us physically. When I say physically, I mean holding a piece of it in our hand. But anyway, that is my Geo-Rant for today, and I hope you learned something.